Today we're going to provide an overview of pesticide water quality monitoring in Minnesota. So that'll include a background of our activities at the MDA and provide an overview of where we're monitoring and what we're finding in both groundwater and surface water. As mentioned earlier, the Minnesota Department of Agriculture is the lead state agency for the registration and regulation of pesticides, meaning that for registration, we allow what's able to be used in the state, and for regulation, we have a pesticide management plan that lays forth the activities that we're going to do. And included in that plan is a large component of water quality monitoring. And this monitoring is intended to be very broad in nature, and we have a long-term data set. So we want to have the data in hand when we need it, if we need to make decisions to have that scientific basis for any potential changes in use in the state. Ultimately, the goal is to use pesticides in a manner that will not cause unreasonable adverse effects on the environment. Part of what makes our program unique is that we have a nationally recognized laboratory in-house. You can see the graphic here. The black line is the number of pesticide analytes that we can analyze for each year over time. You'll see a significant jump happened in 2010. This occurred after some dollars from the Environmental Trust Fund, as well as the Clean Water Fund, allowed for the purchase of a couple of new instruments. So that resulted in a large increase in what we could analyze for. Since that time, our lab has continued to work with these instruments to add a few chemicals every year to a point where we're up to 181 different pesticide analytes in 2020. The blue line is what we're detecting in surface water, and the green line is what we're detecting in groundwater. So while we continue to add chemicals, what we're actually detecting in water has been pretty stable over time. In addition to continuing to add chemicals, we're also able to push our method reporting limits lower. So it's an increase in both the number as well as the capability of what we're doing. We have an analyte selection process that prioritizes chemicals that are likely to be detected in ground and surface water as a result of routine use in Minnesota, as well as it prioritizes chemicals that has the potential to pose the most risk to both human health and to aquatic life. I should just mention, majority of our funding comes from fees paid on the sale of pesticides in the state, as well as some dollars from the EPA and some Clean Water Legacy Amendment dollars to help support that equipment that was purchased in our laboratory. When we talk about what we analyze for at the lab, again, we had 181 analytes last year. 42% of those analytes are herbicides. An additional 19% are herbicide degradants or breakdown products. We also have a large number of insecticides and fungicides, as well as breakdown products of those compounds as well. So we have a very broad suite of pesticides that we look for, and we have a lot of information from those pesticides. So the basis of this slide is to say that pesticide data is very messy. When people often ask us for pesticide water quality, it's important to recognize that what we're collecting is actually 181 different chemicals, all of which have different properties in the environment. So how long they'll persist in the environment, how soluble these products are, or if they tend to stick with soil. So we really have to look at individual chemicals separately in order to give an answer on how, what's pesticide water quality like today. We also recognize that there's variable use for all these different products, and that use not only varies by region across the state, it also varies over time. So as we analyze and present this data, it's always important to kind of look at it in the scope of how has use changed over time as well. In terms of surface water, we have very seasonal detection patterns. So we always target the worst case scenario, meaning that we want to collect samples soon after pesticides are applied, and we want to collect that first flush off the landscape. So there is some seasonal variability to it, and we know that we're in the worst case scenario. Finally, our data set, there's many non-detections, and we have different groups of pesticides within our suite. We have a number of pesticides that we never detect in water. We have a handful of we have another group of pesticides that are detected infrequently in less than 10% of the samples. And then we have a handful of pesticides that are detected in greater than 50% of the samples. So again, how do we find clarity in all this noise? So to interpret the data, we have to use the appropriate reference value to evaluate risk. So detection alone in our water resources does not signify risk. So when we look at these reference values, it's important to note that they have both a concentration component, a numeric value, as well as a duration. So that's the exposure period. And to do a true risk assessment, you need to evaluate both of those parameters. In the case of our reporting and what we'll see today, we do a lot of screening of our data using that numeric concentration component of the reference value to, again, identify those compounds that have the greatest risk to our water resources. And lastly, when we're calculating trends, we want to ensure the data is consistent over time. So as we continue to push our reporting limits lower and lower, we want to make sure that we're using a single historical MRL for that time period of data, as well as to make sure that our monitoring networks are consistent over time. Within our pesticide management plan, we developed these pesticide monitoring regions. These regions allow us to collect the data and assess it and report it regionally. There's some benefits to doing this in that, as opposed to doing it trends for an individual site, collecting and analyzing this data regionally allows us to cut out a lot of the noise of the data that you may see at any given site, as well as to extrapolate our findings to a broader area to represent that region. So you'll see trend maps later that have these boundaries across the state. Given this was a Twin Cities group, I wanted to present some non-agricultural pesticide water quality data. So I went into our sales database and I found the top 3 selling non-agricultural pesticides in the state. So from an active ingredient, the way we look at data and report data, it's 2,4-D, MCPA, and glyphosate. I provided some examples of common products that have these active ingredients in them. You may recognize some of them again, and it's important to note what we report on is the active ingredient. So the products that are shown here are no way endorsed compared to any other products, as well as if you're looking at the shelf, the product name that you're buying is not what we report in our data. It's, again, the active ingredient. We'll move next to our ambient groundwater monitoring program to kind of give what we're doing and what we're finding. Our groundwater monitoring at the Department of Ag began in 1985, so we're approaching 40 years of water quality data. We want to target the most sensitive areas, and if you look at the map on the right, you'll see a density of sites in central Minnesota, and these areas are characterized by sandy soils, a lot of row crop agriculture and irrigation. So we have a high number of sites in central Minnesota, as well in southeast Minnesota with the karst geology. We have a network of domestic wells, as well as springs in southeast Minnesota. The rest of the state, we target shallow monitoring wells. So the idea with that is we want to interface with the groundwater that was impacted most recently by activities at the surface. In southeast Minnesota, with the domestic wells and the springs, we tend to get a little bit deeper water from deeper aquifers, but those are the access points that we have. Within each PMR, we also target the most sensitive areas. So if you look at south central Minnesota, for example, we target areas that have sandier soils and have the greatest potential to have leaching of pesticides into groundwater. Our networks were redesigned in 2000. That led to many new sites, many new wells, and some nested wells. The whole network is designed to track trends, and we have a long-term data set. So the idea with this is that we set up at a site and we're there, a long time, which allows us to make sense of what's happening with the data, as well as to give context for any new findings that we have. Groundwater reference values. So this again is the numbers that we screen our data against to kind of determine what compounds may be posing risk to, in this case, for human health as a part of drinking water. We rely on the Department of Health to set these reference values. For the Department of Agriculture collects the data, we analyze it, we report it, but we partner with the Department of Health when we, again, go to that risk assessment level. There are many different types of groundwater reference values, and for today's presentation, I just defer you to the Department of Health for the nuances and the differences between each of the reference value types. This is a pie chart that shows the 2020 groundwater detections by type. So we had 39,000 pesticide results in 2020, just over 1,000 total detections. About 2/3 of those detections were breakdown products of herbicides. An additional 21% were herbicide parent products. So if you look across our data set, about 90% of what we're detecting for pesticides in groundwater is herbicide and primarily herbicide breakdown products. 8% of our detections are also insecticides, many of which of those insecticide detections are a result of a specific class of insecticides, the neonicotinoids. And we'll go into that a little bit later in surface water primarily today. We also, infrequently detect fungicide and fungicide breakdown products. If we just give some highlights from our 2020 annual report, of the 180 or so different pesticides that we analyzed for, we detected 45 different pesticides or pesticide breakdown products. Metolachlor ESA, this is a breakdown product of metolachlor, was the most frequently detected analyte, and we got some additional slides related to metolachlor ESA later. Good news on glyphosate, this is the active ingredient in Roundup. We did not detect glyphosate or the primary degradant in groundwater. We did have 3 detections each of 4-hydroxychlorothalonil and 3 detections of total cyanazine that were greater than 50%, but all of those detections were below the reference value. So there are some compounds, and in this case, we'll go back and do some additional monitoring to see how those concentrations change over time. As part of the pesticide management plan, there's a designation for groundwater. It's a common detection pesticide, and this designation is made by the Commissioner of Agriculture. And after these compounds are designated, it requires long-term monitoring and analysis of data, and as well as a component that includes outreach. So we have an education and promotion team that develops best management practices and other advice on how to use these products safely, as well as the distribution of this information to whether it's farmers who are using the products or custom applicators or co-ops. We want to create the information and get it out to the people that are using these pesticides. And again, the idea is to be proactive on this designation and to have those materials ready to ensure that these products can continue to be used safely in the state before it gets to be a problem. The 5 herbicides are acetochlor, alachlor, atrazine, metolachlor, and metribuzin. And for common detection, we look at both the parent and the breakdown products when we determine common detection status. Like I had mentioned previously, when we look at pesticide water quality data, we always have to put it in the context of use in the state. And over the last decade, we've seen a large increase in the use of herbicides in the state. So for acetochlor, metolachlor, and atrazine, from 2010 to 2019, we've seen a 2 to 3 times increase in the amount of pesticides sold in Minnesota. There's also been a 7-fold increase in metribuzin, but admittedly, metribuzin total sales in 2019 were less than 200,000 pounds. So while it shows the greatest rate of increase, overall use is much lower compared to these other products. In addition, alachlor, this is a herbicide that is actually no longer registered in the state. We continue to monitor for it, and we're showing downward trends in that product. This slide is kind of busy, but we'll walk through it together. So on the left-hand side is detection frequency for these 5 common detection pesticides. A few things to note on this graphic. First of all, metolachlor or metolachlor breakdown product is found in about 90% of the samples that we take in the state. The next line there that's kind of increasing then has stabilized recently is acetochlor. And we've seen downward trends of atrazine and allochlorin detection frequency at the statewide level. The compound on the bottom there is, again, metribuzin. That's the compound with the lowest sales in the state. But it appears as well as that we're seeing a decreasing trend in on that product as well. The right side of the graphic shows concentration. So what we're presenting here is a 90th percentile concentration. And for reference, the reference values are on the bottom right of this slide. So the line on top is the 90th percentile for metolachlor, and it certainly has increased over the last decade or so. So the concentration at the 90th percentile has approximately doubled in the last 10 years. When we look at that in terms of the reference value, we're less than 0.5% of that reference value. So while we calculate a increasing trend, it's always important to have the context of the reference value when you're interpreting the data. A couple of good news is on the allochlor trend is decreasing downward as well. And for all of these 90th percentile concentrations, all of these are very low when we look at that reference value. So kind of the takeaway is that we find a lot of pesticide and pesticide breakdown products, all the concentrations for the most part are very low compared to the reference values. I wanted to provide some context to show differences across the state that we see regionally. And to do so, I looked at the 2020 groundwater metolachlor maximum detections in the state. So that health risk limit, that drinking water reference value is 300,000 nanograms per liter. And you can see across the state, we do see differences in that maximum concentration. In this case, our maximum occurred in northwest Minnesota, and our second highest detection occurred in central Minnesota. Across southern Minnesota, our concentrations are very, very low. Again, we're nanograms per liter, so this is part per trillion. If we look at a breakdown product of metolachlor ESA, this health risk limit is 800,000, and the maximum concentration in Minnesota was 13,000 in central Minnesota. The second highest maximum was in east central Minnesota. Again, across southern Minnesota and western Minnesota, detections are very low when we scale it up to that reference value. I wanted to provide this slide. It's kind of an example of what information is available in our annual report. So for each of the common detection pesticides, it has its own section in the report, and we calculate and present these regional trends. Part of this as well is that, again, to get back to how messy our data sets are. And if you're interested in a particular chemical, the information is certainly available to evaluate. Just for quick help in looking at this graphic, metolachlor parent is in the left column, and the two breakdown products, metolachlor ESA and OXA, are in the second and third column. As we go across the rows, the median concentration for that region is on the top, the 90th percentile is in the middle, and the bottom row is detection frequency. So when we look at these regional maps, red is showing an increase in trend, green is showing a decrease, kind of the gold is showing no trend, and the gray represents regions in which we don't have enough positive detections to calculate the trend. So we are seeing increasing trends for several regions, for several of these statistics. We are seeing a downward trend at the median concentration in south central Minnesota. So again, if you're interested in any kind of information like this, we have a lot of these graphics prepared in our annual report, and I'll provide a link at the end. If we remember back to that initial slide, looking at detections in 2020, about 8% of the detections were insecticides. And of the insecticides, most of these detections are caused by a class of insecticides called the neonicotinoids. You may be heard of these. They're been in the news a lot related to pollinator health. But on a statewide detection frequency, we have detection frequencies from 8 to 19% across for statewide. When we look at the maximum concentrations in groundwater, you'll see that all of these maximums are below the reference value for human health consumption. When we talk about the neonicotinoids in terms of surface water, it's important to realize the aquatic life benchmarks for the neonics are extremely low. So we'll discuss much more on clothianidin and imidacloprid in a bit, but we are detecting these neonicotinoids in groundwater. The last piece on groundwater today is kind of looking at our urban monitoring results. We have 20 wells in the metro area that we sample for pesticides. And the table on the right is admittedly messy, but I wanted to show every compound that we detected in this network in 2020. So we have what we detected as the first column, detection frequency in the second, and the last column on the right shows the maximum concentration as a percentage of the reference value. The compounds that are bolded are compounds that we only detected in our urban groundwater monitoring networks. So when we look outstate and primarily the agricultural areas, we're not seeing these. And if we look at the products that fall into that category, it makes sense on how they're used in the state is that we would have more use in an urban area. In terms of what we detected, the two metallic degradates were the most commonly detected compounds, and all of the detections are low compared to the reference value. When we think back to what our top 3 non-agricultural pesticide sales were, good news is that 2 of the 3 of those compounds were not detected in urban groundwater. The third one, this MCPA, we had a single detection in our urban monitoring network, and the maximum concentration was less than 2% of the reference value. So again, the products that are used, the top 3 non-agricultural selling products in the state, we're not seeing in groundwater, we're seeing very infrequently in urban areas. So kind of the summary takeaway message is that we see a pesticide, at least one pesticide compound detected in about 90% of our pesticide monitoring wells. And secondly is we seldomly have exceedances of reference values for groundwater for currently used pesticides, but they have occurred. And in the case of if we do have a detection over reference value, we go back and do some additional sampling at that well and try to do some investigation to see if something happened nearby that may have caused that higher detection. Next, we'll shift our focus from groundwater to surface water monitoring. Our surface water monitoring program began in 1991, and you can see on the map on the right shows our monitoring locations, and the physical location where we collect the sample is shown by that array of symbols, and the watershed that contributes to that monitoring point is showed with the gray shaded regions. The darker gray represents approximately Huck 8 size watersheds. And we do sample the Minnesota and Mississippi rivers. We show a lighter shade of gray for those watersheds, just given how large they are across the state. Again, we focus primarily in agricultural areas, but we do have an urban monitoring network that's been in place since 2007 in the Twin Cities metro area. Our surface water monitoring, again, we want to target the worst case. So what does that mean exactly? So we want to collect samples when pesticides are being applied. And that occurs, our monitoring season occurs from May 1st through the end of August. And we break up that collection period into 2-week collection periods as well. And within each 2-week collection period, we want to target runoff periods. So the idea is that pesticides are being applied throughout the summer, and we want to always be there when we get that first runoff coming off the land surface. Within our monitoring network, we use a tier system, and we increase the frequency of sample collections at sites that have had a detection over reference value in the past 3 years. So if we have a higher detection, we intensify the monitoring and we stay there for at least 3 years to make sure that it doesn't occur again. For surface water as well, we have a partner. The MPCA is the agency that develops the statewide water quality standards, and ultimately they're the ones that make the formal decisions for the determination of impaired waters. So again, we collect the data, we analyze the data, we report the data. We have an annual meeting with the MPCA where we sit down and go over all of the pesticides, and they're the ones that ultimately makes the calls on impairments. To provide some quick reference, so in 2020 we had 59 locations, and we conducted over 600 sample collection events in the state. Surface water reference values are a little bit different in that we have two sources of those reference values. So the US EPA has aquatic life benchmarks, and for most pesticides, they have aquatic life benchmarks. And within those benchmarks, there's different categories. So whether it's fish or invertebrates or non-vascular plants, when we screen our data, we always take the lowest applicable reference value, regardless of what group it comes from. In the case of a state's water quality standard, we always use the state standard to assess the data. Also worth noting that in order to have a water quality impairment in Minnesota, we have to have a state standard available to use for that determination. In the world of state standards, there's both chronic and maximum or acute standards. And again, we have to look at that duration component as well. The chronic standards are typically have lower concentration components, but that duration piece is longer. And for pesticides, the chronic standards have a 4-day duration component associated with them, whereas the maximum or acute standard, any grab sample over that maximum can result in a water quality impairment. This pie chart shows the total pesticide detections by analyte type in 2020 in surface water. So for surface water, we had almost 75,000 water quality results in 2020 and over 6,000 detections. 47% of the detections are caused by herbicides, and 45% again are caused by herbicide degradants. So when we combine those, again, about 90% of what we're detecting in terms of pesticides in surface water are herbicide and herbicide degradants. A much higher fraction of the detections in surface water are of the parent products themselves. We also have about 4% of our total detections were insecticides and 4% were fungicides. As we get into the data here, you'll recognize that the insecticides have a much lower detection frequency, but the water quality reference values for the insecticides are very low. So when we start to screen our data with that numeric component of those reference values, many of the insecticides really start to stand out in terms of potential risk to our water resources. In 2020, again, of the 181 compounds that we look for and analyze for, we detected 73 different pesticide or pesticide breakdown products. Hydroxyatrazine was the most frequently detected analyte. Overall, again, of those 75,000 or so pesticide water quality results, we had 121 detections that were greater than that numeric reference value component. When you look at the data even closer, you'll see that a few compounds really dominate those detections, including imidacloprid, clothianidin, again, both of which are neonicotinoids, and acetochlor, which is a commonly used herbicide in the state. Chlorpyrifos has been a compound of interest for the department for many years. We had 2 additional chlorpyrifos detections, one of which was above that maximum standard at a new watershed without a previous detection, and that resulted in a new proposed water body impairment that came out just last month by the MPCA. If we lower that screening threshold a little bit, so this pie chart shows the number of detections greater than 50% of that reference value in 2020. Again, this is just using that numeric component of the reference value to screen the data. In 2020, we saw 243 detections that fit that category of being greater than 50% of a reference value. 80% of these detections are caused by 2 insecticides, imidacloprid and clothianidin. 3 additional pesticides equate to an additional 15% of these detections. So of all of these detections that are greater than 50% of a reference value in 2020, 95% of them are caused by 5 pesticides. And we have, almost any year we have some infrequent pesticide detections that fall into this category. And you can see there's 5 different compounds that had 1 or 2 detections in 2020 that fit that category. if we think back to, again, to 95% of those detections were caused by 5 pesticides. And those 5 pesticides have been designated by the commissioner as surface water pesticides of concern. So this is a very similar designation as a common detection pesticide in groundwater, meaning that we have to do enhanced monitoring and assessment and reporting on it, and that we're developing materials to provide to producers that allow them to safely use the products. The top 2 are herbicides, acetochlor and atrazine. They're both common detection and pesticides of concern. The last 3 again are insecticides, so that's chlorpyrifos. This is an organophosphate insecticide. It's made the news recently. The EPA has ended all registrations and all use at the end of December of this year. So it'll be curious to see how our results change in the future without any additional use anticipated of chlorpyrifos. The last 2 again are neonicotinoids. These were just designated in 2020 through our the state register notice in that formal process of designation. When we look at pesticide sales for the surface water pesticides of concern, of course, we've already seen atrazine and acetochlor showing that large increase in sales. Chlorpyrifos is kind of an oddball in year-to-year sales. Chlorpyrifos use in the state is highly dependent on soybean aphid pressure. So if you look at 2019 versus 2010, sales were actually down in 2019 compared to 2010, but the 2 previous years sales were much higher than they were in 2019. Again, with the EPA changing the registration status of chlorpyrifos, ideally the detections in surface water should stop if there's no additional use in the state. The bottom graphic shows the Minnesota pesticide sales for those 2 neonicotinoids, imidacloprid and clothianidin. These 2 products are kind of a challenging as well for us to calculate sales on. Most use of these products in Minnesota are in the form of a seed treatment. So prior to corn and soybeans being planted, the seeds are treated prior to planting. When they're used as a seed treatment, it's the seed itself is considered a treated article, and therefore it's no longer considered a pesticide. So we don't have good sales data on those 2 products that are used in the context of seed treatment. To give some context, we have over 15 million acres of corn and soybean farmland in the state. It's estimated that over 90% of those corn acres are planted with a seeded treat, and over 40% of the soybean acres receive some seed treatment. So we believe it's a function of, we have a lot of use, basically in all the agricultural areas across the state of these 2 products. These graphics they show the statewide detection frequency on the left for these 5 pesticides of concern. If we look at the graphic on the left to start with, again, detection frequency, acetochlor and atrazine detection frequencies are increasing. Again, when we compare that to those sales graphics, it's not entirely surprising that we're detecting it more in surface water as use increases. The red line in the middle with the triangles is clothianidin. So you can see in recent years, we're seeing an increase in detection frequency of that one as well. Chlorpyrifos and imidacloprid detection frequencies are much lower. But again, the reference values for these 2 compounds are very low, meaning that almost every detection of these 2 pesticides are either approaching or over a water quality reference value. If we shift our attention to the right graphic, this again is showing the 90th percentile concentration at the statewide level. And if you could focus your attention at the insert box on this graphic, you could see the concentrations or I should say the reference values for each of these compounds. So for acetochlor, atrazine, and chlorpyrifos, we have state standards developed for these 3 pesticides. Clothianidin and imidacloprid, we rely on the EPA aquatic life benchmarks. The range of these reference values goes from 10 nanograms per liter or part per trillion for imidacloprid to 10,000 for atrazine. So in order to get these to graph together, we scaled the 90th percentile to that reference value. So in this case, if you're at 100% of your reference value, it means that our 90th percentile concentration is over that that reference value. And in the case of clothianidin, the 90th percentile has now exceeded that US EPA aquatic life benchmark. The second line that's showing an increase is acetochlor. Again, our 90th percentile concentration continues to increase with acetochlor over the last decade, and now to a point where we're over 50% of that state standard, the chronic standard for acetochlor. Again, the other three at the bottom there, the detection frequency is quite low on those, and we'll go into these compounds specifically showing the actual number of detections as opposed to this 90th percentile concentration. And again, it's worth noting with acetochlor, the highest concentrations that we see is that first flush after it was applied to cornfields. And our monitoring is set up in a way that we, at those locations with the previous detection over a reference value, we go back approximately 4 days after that initial sample to get a second sample to do that duration assessment. And in almost all cases where we're over a standard with that first sample, we're able to confirm that that concentration has dropped dramatically as the river's levels drop. We're far below the state standard on that second sample collected 4 days after the first. This map shows the pesticide water quality impairments in Minnesota. So currently there are 15 different impairments in play for currently used pesticides. 14 of these impairments are caused by chlorpyrifos. We do have one acetochlor impairment in the state as well. Again, these impairments are designated or proposed by the MPCA and they're approved by the US EPA. And in order to have an impairment, we need to have a state water quality standard. For a note on chlorpyrifos, you can see these impairments are pretty widespread across southwest Minnesota as well as in northwest Minnesota. We've had a couple of impairments. I wanted to take a few minutes just to kind of show the variability in what we see in our data set and when we're having detections. So this slide, we looked at all of the detections that are greater than 10% of the acetochlor standard. And on the bar graph on the left shows these detections by year. And the portion of the bar that's gray represents detections that are greater than 10%, but below 50% of the standard. The orange and white checkers are detections that were greater than 50%, but below the standard. And the portion of the bar in red represent detections over the standard. So if you look year to year, the greatest variability is in that lowest category of 10 to 50% of the state standard. When we get to that 50% threshold and that detection is greater than standard, we've come to a point where we're pretty consistent with the number of those detections that we're seeing in any given year. And again, for the herbicides, it's important to note that when we have high detections, in almost all cases, that follow-up sample shows a dramatic drop in concentration. When we look at the same data set since 2007, and if we just include the detections greater than 10% of the state standard, you can see that the vast majority of these detections for acetochlor occur in May and June, which again aligns with when these pesticides are being used in Minnesota, as well as the majority of these detections occur in storm flow. So these are periods when we actively have runoff occurring off the landscape and into the rivers. So if we're thinking about acetochlor worst case scenarios, it's May and June during runoff collection period. Next up is atrazine. Again, on the left shows the number of detections greater than 10%. And you can see the greatest variability, again, is in that lowest tiered category of 10 to 50% of the standard. The good news with atrazine is that detections above the standard is pretty rare, including in 2020, we did not have any detections over the atrazine standard. If we look at timing of detections for atrazine, June is really the month that has the greatest number of detections greater than 10% of the standards when we're looking for atrazine. And again, storm flow dominates that those detections. Chlorpyrifos, again, we've had 89 detections since 2005, and the majority of those detections have occurred in western Minnesota, in southwest and south central Minnesota. And the map on the left shows really southwest Minnesota is the area where we're seeing the most chlorpyrifos. The graphic on the right shows, again, variability in the number of detections per year, and we had just 2 detections in 2020. Chlorpyrifos is the oddball in terms of detections. We detect 3/4 of our detections in August, and the majority of these detections occur in base flow and there's no runoff occurring. So it's really unique to our pesticide data set, and it certainly implies different transport mechanisms into the rivers as opposed to the classic application and runoff scenario of the other pesticides. For clothianidin, this is, again, the neonicotinoid insecticide. We've had over 400 detections since 2011, including 94 detections in 2020. The takeaway for clothianidin is that where we analyze for it in agricultural watersheds, we're detecting clothianidin, and we are not detecting clothianidin in urban areas. The graphic on the right shows the number of detections by year, and it shows an increase in the last few years of detections. And for reference, the benchmark is 50, so that the area of the bar in red is showing the number of detections over a reference value. For clothianidin, 88% of the detections occur in May, June, and July. Again, if we think about agricultural activities in Minnesota, this is when we're planting corn and soybeans in the state. So we're planting these seeds, and they're showing up in our water supply, or in our surface water, rivers and streams. 90% of these detections occur in storm flow periods, much like the herbicides. If we talk about imidacloprid, same scenario for clothianidin is that we're seeing imidacloprid in almost every agricultural watershed where we're analyzing for it, as well as in the urban sites. Detection frequencies for imidacloprid are very comparable when we look at our urban versus our regional data from the agricultural areas of the state. We've seen a large increase in detections in the last couple of years. A key function of that is that our historical method reporting limit was 20. In 2018, we dropped down to 10. And then since 2019, we're able to analyze or report detections greater than 5 nanograms per liter. So when we look at this bar graphic over time, it's only fair to compare portions of the graphic that's the same color. You can see we have a lot of detections between that 5 and 20 category that historically we weren't able to say much about, but it's anticipated that we had a lot of those detections in those lower concentrations previously. For imidacloprid, 85% of the detections occur in May, June, and July, and over 80% of these detections again occur in storm flow. So when we have water running off the surface into the rivers and streams, that's when we're detecting imidacloprid. If we look specifically at our urban surface water monitoring network, we began in 2007. In our current locations, we have 4 locations. So we have Bassett Creek, Battle Creek, Minnehaha Creek, and 9 Mile Creek. All of these are located in the Twin Cities metro areas, and we often get requests to do urban monitoring in Rochester or Duluth or other cities. And we stick to the Twin Cities areas because these watersheds are almost entirely developed. And in the case of Rochester, we have a lot of watersheds coming into the city that's still farmed. So we rely on that Twin Cities area for our urban monitoring networks. Again, this is a very busy slide, but this is everything we detected in our urban monitoring network in 2020. So a few takeaways again, the compounds in bold are compounds that we only detect in our urban monitoring network. Again, when we look at these products specifically, it's not surprising given how they're used that we would detect them in an urban environment compared to an agricultural environment. A few takeaways from this. So 2,4-D in a breakdown product of atrazine was detected in every sample we analyzed from our urban network. Again, those 3 top selling non-agricultural pesticides, including 2,4-D, MCPA, and glyphosate, are amongst the most commonly detected compounds in our urban monitoring network. But it's important to note that the maximum concentration was less than 3% of the reference value for all these compounds. Additionally, we've had 3 insecticides detected overall reference value in our urban monitoring network in 2020. These compounds have very low reference values, and when we have a detection again of these insecticides, we're always a concern in terms of when we compare that to the reference value. We often get questions on if we do lake monitoring, and we do lake monitoring with our National Lake Assessment. This is a EPA program that the MPCA collects samples for. It happens every 5 years, and they're randomly selected lakes across the state. So we often provide bottles for them to go out and collect samples, and our lab analyzes it for it. And we have a nice data set that's statistically randomly selected locations. And this upcoming round will represent the 4th round that we have, so we're starting to build some data that we can say what's happening over time. We also have a network of rainfall monitoring stations in the state. So we have one in Northwest, one in St. Paul, one near Mankato, and one in Rochester. We often get questions about how pesticides are moving in the atmosphere, and by having these rainfall collectors, we're able to provide some data when people are curious about a particular product on what's just moving around in the atmosphere. So kind of the simple summary from the surface water section is that we have a strong seasonal detection patterns in Minnesota related again to when pesticides are applied and used in the state. We see a spike in concentration and detections during that initial runoff period. Pesticide concentrations are very dynamic, and they decrease rapidly after storm events in our rivers and streams. We're seeing an increasing statewide detection frequency for a few products, including acetochlor, atrazine, and clothianidin. And when we look at the pesticides not designated as pesticides of concern, we seldomly have concentrations that exceed reference values. So we still have a very broad net of the type and number of pesticides that we look for, but there's only a handful of pesticides that are detected over that numeric reference value, the numeric component of the reference value at any frequency. All of our data is released in an annual report. If you go to the Minnesota Department of Agriculture's website and type in monitoring, all of our historical reports are available, as well as all of our data is fed into the National Water Quality Portal. It's a website that allows users to gather information on all water quality parameters, and it's used by the USGS, many different tribes, different states, as well as local organizations. So it's a really great reference if you're interested in a particular pesticide to gather a lot of information that's already been analyzed and paid for by other people. So with that, I guess I'll open the floor to questions.
Thanks, Dave. That was really useful. I knew very little about pesticides, and I think I've learned a lot. So folks, feel free to chime in the chat or raise your hand. I'm happy to have you ask your question out loud, but we'll start with Matt Koshin. Can you define reference value? How is it related to chronic or acute human health effects?
Yeah, so reference value, the way we use it is that it's a collective of the state standards for water quality for aquatic life, benchmarks, drinking water values. So it's just our broad term. For state standards, we have both the chronic standards, which again, for pesticides have a 4-day duration component for aquatic life, and the maximum standards is just that single value, a single point in time can result in an impairment. When we screen the data, like I said, we always use the lowest applicable reference value. So in the case of standards, it's always that chronic, and for the aquatic life benchmarks, we always pick the lowest value as a conservative approach to use for screening our data. So reference value for the MDA is just a collection of everything, and then when we get down to the specifics, we break it down for the drinking water values as well as surface water reference values.
Great, thank you. And again, folks, please put your questions in the chat. I have a question. Maybe I misunderstood because there's a lot of graphs, but it seemed like for groundwater, there were some downward trends in pesticides, even as sales were increasing, or maybe it was just that maybe the trend wasn't going up and was more flat. Why do you think that is in groundwater that's happening?
Yeah, so a couple things. So the Alachlor was that product that is no longer registered. So that was one of the products that was showing a decrease. So that's kind of behaving as we would expect as we get further away from use. Atrazine was the other one that was decreasing for detection frequency. And we think it's a function of the regional components of our data. We collect a lot of data in central Minnesota. And when we show statewide data, a lot of that data is from the central and southeast are shown or dominate that data set. We think a lot of the increase and atrazine use is occurring in southern Minnesota and western Minnesota as well. So statewide, we're showing a decrease, but there may be nuances regionally when you look at that data closer.
Got it. That's helpful. Another question I had when we talk about sampling, so you're not reporting individual site trends, you're doing it by region. How do you ensure it's non-biased when your sites shift over time? Do you subsample or?
So for surface water, our protocol is to stay at a site for at least 3 years if we have a detection over a reference value. Of our 59 locations, I think probably 50 or so are in our tier 2 category. So that means we've had at least one detection over reference value in the last 3 years. When we include the neonicotinoids, the sites where we're seeing these concentrations, we're basically stuck at in terms of our monitoring design. Many sites, and that's not a bad thing because we have records for many sites that go back to the early 2000s now. But we don't add a lot of sites because we don't have the capacity in our lab to continue to expand our program. So the sites that we have in our networks, in many cases, have 15 years or more of data from them.
Got it. Okay. Thank you. Anybody else have a question or a comment? Dan Henley says, how do you evaluate the major rivers like Minnesota and Mississippi compared to some of the tributaries since the large rivers serve as an aggregate?
Yeah, so historically we focused kind of at that Huck 8 scale. We added Mississippi River at Gray Cloud Island and the Minnesota River down near Mankato. Concentrations for pesticides tend to increase as watershed size decreases. So what we see in the larger rivers tend to see much lower maximum concentrations, and that's kind of why we only have a limited number of main stem sites. We really want to focus on those smaller watersheds closer to where the application occurs. So again, that's the highest risk as we move up the watershed size.
Great, thank you. Okay, well, I think that we're just about out of time and I don't see any other questions. So thank you so much, Dave. And folks, here is Dave's email address. So I think, reach out if you have any questions or, about individual watersheds. I'm assuming you'd be happy to talk with people.
Yeah.
Great. So thank you. We will be posting this on our website in the next few days. And yeah, I think that's it.